Hey everybody! I wanted to spend a little bit of time reviewing what's going to be on the benchmark coming up so that I could fill in this bubble right there. Um, and so um I first want to say that I know that maybe some other classes have taken the benchmark. This one will be different than maybe your friends have taken that have taken the benchmark in other classes, but that doesn't mean that it's going to be unfair or crazy. Now, I'm going to take this section by section so that you know what we're going to look at. So in terms of the metric system, okay, let's see if I can get this going on here. In terms of looking at the metric system, I'm going to be very fair about this. I'm not going to ask you about all the parts of the metric system. What I'm probably going to do is ask you some specific content questions about um, a singular unit, like um, explain. Um, I'll say pick one unit, and then I'll say explain what this unit measures. Explain why this unit is better than its English equivalent, or why it's um, or what is some of the history behind this unit. So I want you to gather. I want you to have that information at hand. Okay, it's not going to be tell me about each of these things. What do each of them measure? Okay, I'm going to keep it in the context of what you had to do for your own presentation. And then when we talk about sig figs and precision and accuracy, we took those kind of together. So what I'm going to do here is I'm probably going to give you a set of data, and I may actually ask you to do some math with that data, like um, maybe calculate an average, maybe calculate area, length times width. Okay, and so maybe even have you calculate density, mass over volume, because we did the density lab. Okay, but I'm going to definitely give you data. And based on that data, I'm going to ask you to calculate that data using the appropriate sig figs. Okay, so if you need to refresh yourself on using appropriate sig figs, you can either go to the box and dot article here, or you can do my video here about that. If you need to remind yourself how to do math with significant figures, I would come over here to this one and see what the deal is. In terms of accuracy and precision, I think it's important that that kind of goes hand in hand with significant figures. It's a very kind of straightforward topic, but you need a set of data in order to be accurate, to talk about accuracy and precision, or at least some data. So I think that you may have 2 or 3 questions dealing with data and data interpretation and trying to figure out what's going on with that data. Okay, so it's going to be very similar to kind of your analysis for the density lab. Now, as we move over to the right-hand side of the mind map, I will say that one of the biggest things that chemically, as we move forward, that that is important is understanding particles. So it wouldn't surprise me is as we're looking at particles, that the particulate theory and understanding that solids, liquids, and gases are particles and how they interact and what is causing them. It wouldn't surprise me to see questions where I'm asking you to draw pictures of particles and showing how they interact, maybe identifying intermolecular forces versus bonds, okay, or talking about how gases are different than solids. Okay, I'm not going to talk about Bose-Einstein condensates, nor am I going to talk about plasmas. Okay, that was only for the states of matter writing task, so it's not a thing. Okay, but then we can also talk about substances and mixtures. I spent some time talking to you about substances and mixtures in class, trying to make sure that everybody understood the differences, especially in terms of mixtures. Okay, understanding the difference between mixtures. I will say that the hardest thing to delineate between is a compound and a homogeneous mixture. A compound is only one substance. So this is one substance. A homogeneous mixture has several ingredients. So if you know it has several ingredients, but it appears to be all consistent, like milk, soda, gasoline, ink in a pen, those are all made up of different things. It's a combination of different things, has several ingredients. And so that right here is a big deal. Okay, so knowing how to be able to tell the difference between those is something that I want you to do. So let me just make sure. So a compound, if I'm going to write this graphically, okay, compound is all one thing. Okay, they're all one molecules. Now these molecules may have different atoms in them, like water, H2O, 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 whatever. Okay, but it's all one thing. Versus a mixture, which is a homogeneous mixture, which may be water. Here, let me put a line here so that you don't get confused here, which may be water, but that water is now mixed with something else, maybe salt particles, okay, and it's evenly spaced, okay. Maybe if you're at the beach, maybe it's mixed evenly with whale pee. I always say that to my kids. Right, Chloe? Yeah. Okay, so I always say that sea foam is just whale pee coming up on the top. But anyways, but it's evenly mixed, so it appears to be one thing, but it's not. So there's definitely a difference between those. So that's going to be really an interesting part, and it can be determined based on the particulate view of matter. So, and then coming back here, and then physical and chemical changes, that's the last one. This, I can tell you, is again talking about particulate view of matter. If we talk about how particles interact, okay, if we have, let's see, water, and I use water because water is very common. So we have an attraction between water and another water molecule. That is an intermolecular force, and that intermolecular force can be it can be overcome by adding heat. We can add Bunsen burner. Some of you are doing that in the lab. And when we do that, the molecules move faster, and now we can undergo a state change. Now these water molecules, after some time, will become further apart, and they're a gas. They're still water, though. That's a physical change. Okay, as opposed to when we run electricity through water. So now we have water molecules here like this. And what we do is we will run electricity through it. Bzz, bzz, bzz. That's my little lightning bolt here for electricity. And what we end up getting out of that is hydrogen and oxygen, okay, which is nothing like what we started with. This is a liquid, these two things are gases, and that is the difference between a chemical and a physical change. So the chemical changes is here, right? A chemical change is here, where we have the bonds breaking, and a physical change is just the forces um, hanging out. This brings up another point, though, is that a chemical change can cause a physical change, because a chemical change is a change in the bonds, and a physical change is a change in appearance. So because you have a chemical change, the substance changes, which now makes the physical change, or makes it change physically. And so it's really kind of an interesting thing that happens. And I've tried to hammer this home in a million different ways. So that's what we get in terms of chemical and physical changes. So you're going to see a lot of open-ended free response questions, data for this part here, for here and here, and then you're going to see a lot of interpretation for this and this here, where you're going to have to answer some questions. Okay, so that is the review of the benchmark. Hopefully this helps. Have a great day.